Hey, it's another week, so you get another video on electrolyzing water. So today, my name is Paul Seaver. My company is Palm Beach Springs Water Company, and that's what I do for a living is electrochemistry. And in context, I mostly just work on subjects that have something somewhere along the line to do with the water, not necessarily just consumption. Although I'm kind of keeping these videos in the context of consumption. Because mostly, anybody in industrial pretty much understands a lot of this stuff. I don't have to explain nothing to them. They can explain it better to me. I don't build the truck, I just drive it. You're getting everything from the working man's, the guy who applies it, the guy who uses it, the guy who figures out the systems that's needed for a particular environment. You're seeing it from my point of view, not from a lab point of view. So this is a very simple point of view. I don't have a college education. I'm not a chemist. I'm not a PhD. So you're going to get, the working man's version here. So don't hang me for it. All right? This is for all of us to understand. So people don't understand, how do you apply an electrical charge to water when all your life you're taught to keep the two things apart? So yeah, this is a whole different thought process here. So the first thing that you have to understand is this. Water is pure energy. That's all it is. It's pure liquid energy. But it's energy that's stored in very, 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 very small spaces. And it can't accumulate as a single charge, like your battery or whatever, or when you have electricity piped to your house. Wired to your house. So it can't store the charge as an accumulated volume. Each charge is individual and is insulated by the H2O that it's dissolved in itself. So I just kind of switched subjects on you a little bit there, because what I wanted to say is that H2O itself is not what we're talking about. So you don't apply an electrical charge to H2O. You're applying an electrical charge to the content that is dissolved in the H2O, what most people refer to as TDS, total dissolved solids. Those in electrochemistry are not a problem. Those are your tools. Those are worth their price in gold. So you're using each and every component that you want in that water, and you're able to influence it in electrochemistry. That's called increasing its potential. All right, so you're able to increase its energy to utilize it for greater things. So that's all it is. And electrochemistry is no voodoo science. It's think about your car. Okay, so you have an alternator, you have a battery, then you have all your components that are run by those things. So we all understand that. So that's electrochemistry. You have a generator that's charging up a aqueous medium, in this case a very toxic one, sulfuric acid, and is building a charge, but in this case it has a way to store that charge. It has components within that case that help store and build that charge into one charge that you can use. So it's a different variation of electrochemistry, but it is electrochemistry. And most of the gases and things, that are synthetically created, most of those are created by electrochemistry. So they're zapping power into a raw material, causing a reaction, bleeding off a gas, and then they collect the gas and concentrate it into a commercial form. So that's all electrochemistry too. All your gold plating is electrochemistry. All your powder coating is all electrochemistry. All these things are electrochemistry. So the only difference is we understand these things because we can see these things. Okay, you can see paint stick to a surface with a bond. You know what I mean? You can see some of these other things that I just brought up. You can see those things happening in front of you. So in water, you can't. You can't see it. You can't feel it. You can't. Well, you can taste the difference if you know what you're looking for. But you have to understand it's all mathematics. It's the mathematics of applying energy to the content in water. So water itself, going back to that, being pure energy, was the first molecule formed after the Big Bang. So the Big Bang is the origin of energy, okay? So the Big Bang assigned either a positive or a negative charge to everything that was created, including water. So water is created by protons and electrons, right? Protons got a positive charge, electrons got a negative charge. So when you have one molecule of water, Mother Nature automatically forms another molecule of water by transferring a proton. So now you have an acidic and you have a basic. Together you have a neutral. So everything in Mother Nature has to neutralize. You have to remember that rule. When it comes to water, when it comes to electricity, you know, you think about statics. Why do you have the static discharge from something? Because it has an overabundance of one thing and it tries to get rid of it to another, therefore it can neutralize. You know, and this comes into play in manufacturing all the time. Manufacturers know what I'm talking about. You have to have those neutron neutralizers. Can become very important depending on what you're putting in a container. If you're putting something acidic in a container that has a negative charge, your shelf life will go downhill fast. You have to put it in a light polarity, static charged material. And that really comes into play when you're doing stuff like powders and stuff. That's how to keep that static charge from making that powder go. So you don't want that. You want it all to lay down. So if you want it all to lay down, everything has to be compatible. So, however, you know, so I'm not into that equipment type of building. So, but I'm just trying to explain. These are the things that people understand. So water's the the same way. That's what self-ionization is. That's Mother Nature's way of keeping it balanced. But that has nothing to do with content. That has to do with water molecules, okay? So you can't put a charge on a water molecule. It's set. It's done. That's it. It's already perfect. You can't touch it. So now, the only thing you can do is you can dissolve something into that molecule, which is very easy. Okay, why? Because that's what the molecule is designed to do. It's designed to take a piece of material, some kind of component, dissolve it within it, and carry it off somewhere. So that's easy. That's easy to do there. So now, that's called total dissolved solids, right? In a natural occurring environment, you're dissolving salts. So we're not going to get too deep into salts. So the only thing I'm going to include is sodium chloride, because sodium chloride is essential to all life on Earth. You have to have sodium chloride. It's neutral. It doesn't have a pH because it's a salt, but if it had a pH, it would be 7, a neutral 7. So it's providing an equal, balanced amount of content that is needed, period, across the board. So that's why we use sodium chloride in everything that we do, so we can stay non-toxic and safe for all human, plants, and animals. That's a whole other story. So once you have this content in the water that you're looking for, then you have to decide what are you going to do with it, you know? So you could, like we discussed, you could separate it, or you could join it back together. Okay? You can take it from its raw ambient cluster. You could use a lesser system, break it up a little bit. Depending on what you're doing, that might be a better idea, but I don't know where it would be a better idea, but it might be. Or you could go all the way and break everything out. Why does this become important? So, and you can only achieve this through applying electrical power. So if you, we're only at 9 minutes, I guess I could go into this. Once you apply the energy to the ions, like I said before, first you have to decide what are you going to do with them. Do you need 100% basic? Do you need 100% acidic? Or do you need a neutral? So in the context of what we're talking about, we need a neutral. Because we want, in human consumption, you want to be at around 7.4 pH, okay? Now, when in animals, I believe it's the same. In plants, it varies because it all depends on what kind of plant it is. what kind of nutrient you're trying to drive to it. So a lot of times their waters, your irrigation waters can be down like 5.5 pH, So it just all depends, but it doesn't matter. It's still in neutral. Neutral is from 5.5 to 10.5 when you're talking dual polarity electrochemistry. And so within that, let's skip for 1 second here. Within that, you're not in dual, in dual polarity single ion, you're not measuring pH. The ion is neutral. It doesn't change. What you're measuring is the difference in charge that you put on it. Okay? So it's kind of the same as measuring a weak acid, but with a little bit of a twist, because you're manipulating the meter. The meter usually wants to measure the difference in power between pK and pKb, but there isn't any because you're 1-to-1 pKw, right? So because you're bonded 1-to-1, you're not 7-7 pKw at this point. You're 1-to-1 pKw, single bonded ion. So and that's a patented deal. So anybody can dispute it that they want to. So once you have that single ion, you have the ability to put a dominant charge on it. So do you want to go down to acidic or do you want to stay up in a basic? So for human consumption and normal consumption and a lot of things, you want to stay right at neutral but alkaline, right? So because that's what we want for our bodies. So we can do that by just simply putting a dominant negative charge on it overall. Now, say for hydrothermal, this goes back to what we just discussed. So in order to keep scale out completely, you have to change the charge of the ions. So you can put a dominant positive charge on the medium and it will no longer scale. So that's what we do for hydrothermal on that aspect. Just on that aspect, it has to do with scale. It has to do with the electrical charge. That's what the assignment of the electrical charge is for on the hydrothermal unit. The assignment of the electrical charge on the unit for consumption has to do with our pH requirement of 7.4. And the assignment of 7.4 has to do with the gases. So nobody ever went that deep with you on your consumption water before because your consumption water don't have no gases. Right? Well, I mean, it's got the components for your body to make some gases from. Okay, but we already make the gases and we already elevate them, increase their potential by 10,000 plus times because we're applying 10 amps. There's a difference between less than 1 IP and we're at 6.45 IP. So less than 1 ionic product, 1.37 ionic product on average, 6.45 ionic product on average, okay, which is here again equal to 200 degrees when using heat, as everybody understands boiling water. You've got the same amount of energy, you just don't have the heat. So once you do that, okay, we were talking about delivery, okay, so now delivery. So you got everything broke up. Everything's got a light charge. You're in a hydrothermal system. All right, let's break off of human consumption now because we'll dig too deep into human health. So let's switch gears. Let's go to hydrothermal. So now you got your polarity set. You got a dominant positive charge. You can no longer scale. Now, since you have a positive dominant charge, you still have a light charge on all ions, so you're still at 6.45 IP. So what other advantages do you get from that? Okay, so delivery. So now in delivery, it doesn't matter. It doesn't matter if it's a nutrient for humans or plants, a pharmaceutical, if it's a pesticide for distribution, spraying it on a field, or if it's for heat exchange, and well, we'll just leave it at heat exchange for hydrothermal. So let's stay on hydrothermal. So how does this increase heat exchange in hydrothermal? So all the engineers are going to understand this. It's because look at the difference in the surface area. you got 100% of your surface area available and separated for absorption by your content, which is actually holding the heat. So some people say, oh yeah, zero water would never be efficient in a hydrothermal system because there's nothing to hold the heat. If there's nothing to hold the heat, how are you going to transfer the heat? So now, if you have content, it's a fine line. So you can't have too much content. You know, in typical water, you know, they'll get too much clustering, and then it starts to insulate the heat, where the clusters can't transfer the heat fast enough to get rid of it or to collect it, depending on what you're doing here. So it can't transfer it one way or the other because it's insulated. So once you break out all your molecules, there's no way in the world you can insulate anything because you're completely broke out. When you have an increased ionic product that has the ability to absorb and dissolve content within the water molecule itself, then you can separate all your components. When you're neither acidic nor basic, you're not an inhibitor to anything that you're using for a treatment, for whatever treatment you may. Not that you would need that treatment, but in some places you're required to have treatments. You don't have any choice. You have to have it for preventative controls. In those instances, you can use far less because you're not using a treatment that's inhibited by the content of the water that you're mixing it into. And that goes back to what we showed with the cinnamon and clove. You know, that was an extreme on both ends, of course, but that makes the point. So for the average individual to understand what I'm talking about, it's really very simple. Let's think about ice for a second. Everybody understands ice. So the one thing that you understand is the difference between an ice cube and a snow cone. You make the snow cone from the ice cube. You don't make the ice cube from the snow cone, right? So when you take an ice cube, you can change that ice cube's properties because it's water. You can, but the problem is with an ice cube, is you're at 100% total clustering, massive, compacted, zero energy. You know, the wonders of water, right? So now, in order to separate those molecules, which we'd never be able to separate the molecules, but in order to create your little nanostructures, let's say, in comparison, okay, you have to shave it. And you try to shave it and smooth it down to the finest that you can get. I mean, this is a competition between manufacturers to get the smoothest shaved ice, right? And so the smoother you get it, the more absorbative it becomes. You change in the properties. You could never get an ice cube to absorb nothing. That's not what it does. But once you shave that ice cube, you can get it to absorb. And so why? Because you're increasing the surface area. You're breaking everything up, and now things can flow in and flow. It's not actually absorbing into the ice itself, but it's absorbing in between all the clusters. Okay? But so that's a little straight off, but I'm trying to give you a better idea of distribution. You know, so if you wanted to distribute a flavor into a volume of frozen H2O, the one that would be more accepting would be the snow cone, not the ice cube. The ice cube would just take the flavor and it would just run off it, and the snow cone would absorb it. Okay, so here, think about that when you're thinking about heat. So you have a lot more surface area to absorb a lot more heat, and then you have a lot more surface area to exchange that heat. Okay, you have all your ions are balanced in there. They're neither corrosive or oxidizing, and they're non-scaling, so you get to use them to their full potential throughout the entire system. They're no longer a problem for you. Now they're increasing the performance of your system. Okay? And increases the performance of the system so well that you can expect a typical 25% savings on energy consumption alone. Now, this is no secret. This has been out for a long time. Those units have been out for 30 years, you know? But tough sale in the United States. Unbelievable. They save you that much money But the problem is, you know what the problem with that equipment is? It saves you on maintenance, it saves you on chemicals, it saves you on all those things you're buying. So the only one that's really interested in it, the last person that you can get to is the end user on a commercial operation, that actually the one that has to pay the bills. That's the guy who's going to care. And when he finds out that he can save 25 to 45% of his operational costs, he's all over it. There's not a maintenance company in the world that wants anything to do with this equipment. Why? Because there's no more maintenance after you put it on the system. That's why. No more blowdown. So let's talk about, let's switch gears here and not talk about scale. Let's talk about the electrical influence on organics. So now, since you're running a positive dominant charge, you're also creating ozone, chlorine, all hydrogen peroxide, all sorts of things. And then you have the half-life transfers of those things going on. Why? Because you're not just relying on a concentrate treatment that you put it in there, light the fuse, and once it goes off, that's the end of it. You got a generator constantly flooding the system with an infinite amount of fresh gases, fresh hydrogen, fresh reactive oxygen, those things working together to keep the system balanced, right? So you don't have an overabundance of reactive oxygen. Instead, your reactive oxygen is just enough to take care of the loading that it has to take care of, and the hydrogen neutralizes the rest of it, turning into what? H2O. Hell, you're making water. Or you're using water to do things, and then so you're making it back again. But that's the byproduct. It's just H2O. So if you have a unit that is matched to the operation that you need, you can apply the energy correctly, and you can maintain your entire system. I'm going to do a video of the system I have on my home. And I purposely have a neutral batch tank that sits in direct sunlight that is perfectly clean. I don't have to touch it. Don't have to do a thing to it. And let me tell you something. I'm trying to wait for my filters to get dirty enough so that I could make the extreme illustration and show the difference. Show the algae coming in, show the tank crystal clear, and show the circulation filter that's on the tank just being neutralized orange. And then nobody can dispute that. See, that's where we take care of waterborne pathogens and stuff like that. And so we can neutralize all that stuff. Plus, once you electrolyze and you're down to single ion, single molecule, highly charged, depending on what kind of operation you are, say like you're a food service operation, food production or whatever, and you want to have an extra preventative control for things like E. coli. So what particle size is E. coli? It's a half a micron, right? You can filter down to 0.35 micron with no problem at all because you don't have no clusters. 0.35 microns, nothing for this water. Once you start going lower than that, then you can start to pick up a lot of really super small stuff that'll clog up smaller filters. But most of the time, in this, you have most of your organics are coagulating together, and you don't really need anything smaller than a 0.35. And especially, when what you're targeting is half a micron. So you're below that half a micron, so that's an extra preventative control that's non-regulated. You don't have to worry about no chemicals, you don't have to worry about no hazards, you don't have to worry about nothing. You're just filtering it out. And it should be already neutralized anyway, especially once it gets trapped in a filter system and it doesn't have anywhere to move. So that's where it is in sanitation. So everything that you build at the anode. Okay, so in electrochemistry for gases, this is kind of a different subject. You know what, I'm not going to get into gases because it'll get too complicated. We're already on 24 minutes. But everything you build, all the reactive oxygen that you're building at the anode is in the flow. All the hydrogen that you're building at the cathode is in the flow. And so, like I said, it's all balanced. It's perfectly balanced. We balance it by the polarity offset to make sure you got enough reactive oxygen to maintain everything you need and enough hydrogen to neutralize the rest. It's a beautiful, beautiful system. So no scale. And so with filtering out the organics, I kind of missed that portion a little bit. Filtering out, being able to filter out the organics means you'll never have to shut down for a blowdown. Never having scale means you never have to shut down to descale, nor the other maintenance problems that come along with descaling. Okay? Now, I'm not saying that your waters can't ever get overloaded and that you won't ever need a bleed off, because unfortunately that just comes with evaporation, right? There's nothing you can do about that. So if your evaporation rate is very high, and this will reduce your evaporation rate, but every operation is different, okay? So a lot of it has to do with temperatures. But as everybody understands, your makeup water constantly coming in, adding to the concentration of TDS from evaporation, at some point in time, you're going to have to flush the water. Not shut down the system, you're just going to have to get rid of some water. You're going to have to lower that TDS. Now, you could put an RO on it, you could do whatever you want to keep that TDS maintained. So the TDS won't go up as rapidly because we use a lot of TDS in the process, so we're burning a lot of it up. But it's not meant for TDS reduction. It's meant for TDS maintenance, TDS control. You know, and keep the TDS from scaling to the pipes. So that's the last thing you want. A lot of people say, well, look, we can maintain TDS. No, they're not maintaining TDS. TDS is scaling to the pipes. The TDS isn't going higher. It's collecting. And we got all the data and everything with, X-rays and all that other stuff on. We can take one of our systems and actually put it on a system, and through that stored electrical charge, be able to peel the scale off. And so I know that for a fact. I've done it myself on systems. I've done it even on my own system where I had a problem with a flow meter. And I had a flow meter on a basic side, and the static charge that the electronics that was running that flow meter was just collecting the basics like there was no tomorrow. It was a pain in the butt. So and it was all scaled up the sides. And so then I took that flow meter and I switched it and I put it over on the acidic side, cleaned that flow meter right up, never scaled again. So just, the difference. The same thing when I'm doing some pumps sometimes. I got clear lines because I have to see what's going on. So when I get the basic side running through a pump that's plugged into a regular 110 wall, you get scale coming out the other side of it. Change that to a DC pump and it won't happen. But change the polarity, like I just did. I did a video of it, a private video, where I changed the polarity with a different device of the material that was running through that pump to a positive charge. No more scale. Same thing that the electrolyte unit does, but I did it with a little bucket, and I did it on a different level. But anyway, that's how you maintain scale. That's how you work with scale. What you gotta do is you gotta play by the rules of the materials that you're working with. The rules of the material that you're working with is they want to have an electrical charge. So if you have the ability to, I don't know, did I show my machine here? If you have the ability to target things in water individually and give them what they're looking for, you can redirect them. That's all they want. Water will do anything you want it to do, but you have to tell it. You have to have a machine like this that knows how to speak to it. It's not just an anode and a cathode hooked up to a battery and stuck in the water. That is not what we do. That couldn't be anything further from it. But anyway, this video is way too long, and I hope that clears up a little bit of things, at least about the legitimacy and the credibility and the technology and science and mathematics behind actually applying electrical charge to the content of water. So when someone says, oh, you're electrolyzing water, no, you're electrolyzing the content of the water. Until next time, adios amigos.